Our next speaker does what's a sort of a background job in software companies that's often not appreciated by those outside of it. We're highlighting today several background subtle aspects. I've already mentioned the data side. In fact, after Hannah, we're going to go into quite a bit of detail on data, although that may be deferred until after lunch since we're slipping a little bit here on schedule. But Hannah deals in a world of many dimensions. You heard Mike talk about you start with the million-dimensional world of a human language, if you just naively consider every word to be a dimension. You then use dimensionality reduction. We've seen several different techniques of doing that are converging on 300 dimensions. Well, in our software, we've got a problem. We have a curse of dimensionality, to use the term of art in computer science, but it tends to be in coverage. We cover languages. We cover interfaces, Java, RESTful, C++ still. We cover functions. Within the functions, there are sub-functions that vary by language. For example, in tokenization, English is easy. Just look for the white space. It's hard in Chinese. Across all of those dimensions, Hannah's the one that gets to manage our product, cover what our customers need, and to her particular subject that she's going to address today, look at where yet another dimension, the technological dimension, in this case, deep learning, can be applied. Thank you, Hannah.
Thank you, Chris. Good morning. As Chris said, I'm Hannah MacKenzie Margulies. I'm the product manager for text analytics at Basis Technology. The title of my talk today is Deep Learning in Mission Critical Applications, a field-focused evaluation of where, when, and why. And more specifically, I'll be taking a look at really the feasibility of deep learning in these high-intensity situations. And trying to pick apart a little bit of the hype around deep learning that I think we've all been experiencing over the last few years. So if you've been reading the news, you, like me, might have come to the conclusion that deep learning is a silver bullet capable of doing just about anything. And as we can see in this Google Analytics report, we wouldn't be the only ones. So since 2012-ish, we've seen interest in deep learning, mentions in the news, search queries skyrocket. And if we believed all of these headlines, we might think that deep learning can, for example, solve retargeting and reacquisition, cure cancer, suddenly change your life, and revolutionize everything from manufacturing, insurance, healthcare, and agriculture. And this is not to say that deep learning isn't doing many of those things or being applied in all kinds of really, really important applications. Self-driving cars, machine translation, robotics, anti-money laundering, healthcare. We are seeing deep learning provide new kinds of solutions to these problems that are novel. And before I get into a little bit of why we might want to just poke at that idea of revolution a little bit, I want to talk about why we're seeing this huge change over the last 6 years. And I'm going to very briefly touch on 3 areas: algorithm improvements, hardware availability, and results. So in terms of algorithms, I think that the electronic music group Daft Punk says this almost right. Algorithms in the deep learning space have, over the last few years, become simply easier, better, faster, and stronger. They can do these jobs, attack these tasks much more effectively. Thank you, Daft Punk. Second, hardware availability. So these deep learning models are really big, and they take a lot of computational power to train and run. And it used to be that this training could take days, if not weeks. And that time frame has shortened significantly, in part because of the availability of hardware that can support these processes. So we're seeing on-premise GPUs become cheaper, more readily available, easier to get set up, and the proliferation of cloud-based hardware, providing both GPU and CPU infrastructure. And in addition to all of that, we've seen a real major growth in the kind of open source environment supporting this hardware. So libraries that help with the training process and with putting these models out into production. And then probably most importantly, just results themselves. So this graph tracks the number of errors made by the top performing system in a particular competition called the ImageNet Large Scale Visual Recognition, or ILSVRC for not so short. And you may have seen this before. This is a pretty famous graph. Basically what's going on here is that in this competition, a computer is presented in each round, we'll say, with 5 images. Or I'm sorry, with an image. It has 5 tries to correctly predict the subject of that image. And if it fails all 5 times, that's considered an error. So what we're seeing here is how many errors did the winning system make in this competition. And let's see, starting, nope. Aha. Okay, so starting, actually first I'll mention that this is a really hard problem. This is how well humans perform on this task. And so for quite a long time you could see that the computers were not doing so well. But starting in 2012, the winning systems start to be deep learning based systems. And then starting in 2015, we see that they actually start beating the humans, which is really a huge accomplishment, and I think a big part of why all of a sudden we start seeing these headlines talking about revolution, and that this is one of the first times we're really seeing these systems kind of be at the level of, if not exceeding beyond the ability of humans. So to return to my initial question, is deep learning really appropriate for mission-critical applications? Well, as with most hard questions, it depends. So there are real benefits. We just started to look at a few of them, and I'll look at a few more. But there are also real drawbacks. And it really depends on the problem you're trying to solve. So I would contend that at least in my line of work, text analytics, deep learning is not yet the silver bullet that, of course, we would all love it to be. And it should be treated just as one tool within a large toolbox of techniques and approaches to solving these hard problems of human language technology. So I will talk about the benefits because they're very exciting. So 3 areas I'll touch on: back to accuracy, also effort, and pre-processing. In terms of accuracy, this is another fairly famous chart, and the top line, I should say, will eventually curve off. It doesn't just improve forever. I wish it did. But basically what we're seeing here in this graph is that the ceiling for improvement of deep learned models is much higher than that of machine learned models, traditional ones. So if you have data available and you keep feeding the system data, you're going to see significant improvements in your results. And we've seen that firsthand here at Basis. These are some experimental results comparing 2 different kinds of models, a traditional machine learned one and a deep learned one, on the task of named entity recognition. This is where we're picking out things like person names, location names, organization names in unstructured text. We're showing this, these were trained on the same data set in a couple of different languages. And you'll notice that we get a really nice benefit, a boost in results from the deep learned model. And what's especially significant here is that the traditional machine learned model wasn't performing badly. Scores in the 80s on this task is nothing to be ashamed of. However, what's important to note is that statistically speaking, it's a lot harder to get a model to improve from, say, an 89-point F-score up to a 91-point F-score than it would be to improve a model that was only performing in the 40 points range of F-score. So this is very nice. Next, I'll touch on effort. So in traditional machine learning, there's this real art to crafting what we think of as the features that the model will use to make its predictions. And in the world of text analytics, this is things like tokens, lemmas, parts of speech, morphemes, all these smaller qualities of the text. However, crafting these features is a pretty time-intensive process. It's something of an art, and it's expensive. And it's a little bit risky because if you mess it up, there can be significant downstream effects. So in a deep learned model, a big part of what makes a deep learned model special is that it identifies these features itself. You don't have to do it. This requires a different set of skills in terms of getting, choosing the appropriate architecture. But we do see that the time to market with a deep learned model can in fact be significantly shorter simply because there is less of this feature engineering process to go through. Last, I'll touch on the idea of preprocessing. So for any type of machine learning, you have to make sure that your data is prepared correctly. And for us in text analytics, this often consists of things like character normalization, stripping out HTML markers, and as I mentioned, things like tokenization. And as I mentioned also, this can be problematic, something like tokenization, because there's a possibility that you could make mistakes and that there will be these downstream effects. So in this case, I'm going to show a little bit of what those mistakes can look like. So this is a sentence from a movie review in Japanese, and it says, but this family has various secrets. And the word in the box here means various. However, you can see that we've mistakenly tokenized this word into 2 tokens. It should just be 1. And then we've gone and done named entity recognition over this pre-tokenized sentence, and unfortunately identified this falsely tokenized word as a person entity. And this is very sad. However, if we run a character-based model, a deep learned model, this is something that's possible in deep learning but not possible in machine learning, in traditional machine learning, to evaluate and to predict at the character level, no entity, in fact, is extracted correctly. That's the correct answer, and so we can feel much better about our results. Great. So, some very exciting stuff there. Now I'm going to turn to, I'll call it challenges, but just some areas that I think we all want to be keeping in mind as we evaluate the applicability of deep learning for, in these mission-critical environments. I'll talk about 4 areas: suitability, speed, data, and explainability. In terms of suitability, this is the round peg in a square hole problem. So for some tasks, I'm going to say it, deep learning just may not be as good as traditional machine learning. In this case, this is the same graph we looked at before. It really appears to be. However, these are results from a different task. This is for lemmatization, basically predicting the root form of a word based on its surface form. This is an important part of creating an effective search engine. And again, here I'm showing 2 different approaches, one with a deep learned model, and one that's basically just based on a big dictionary. And I will say, we did some more tuning on this deep learned model, and we were able to get it to the point where it outperformed the dictionary in Farsi. But what you're seeing here is that they're extremely close. While the deep learning model performs much better on Korean, it's not actually that different from the dictionary for Farsi. And I can add a little color to this. This new column that says all and unseen, this basically has to do with how well the model performs on words, on all the words that it was presented with, and then how well it performs on words that were not part of the training set or might not exist in the dictionary. And so my point here is really to say that the model and the technique you choose should be based on, again, the problem you're trying to solve. And in this case, it really matters what language you're dealing with. Farsi and Korean are really different languages. And it is possible to produce a dictionary for Farsi that covers the vast majority of the words. However, and I'm not a linguist, but Korean is a language that works pretty differently. It's much more productive, and creating such a dictionary would be very challenging. Thus, the question of suitability, really comes down to these technical and linguistic questions about the languages themselves. The next area I want to touch on is speed. So, at this point, it is still the case that traditional machine learned models are much faster than deep learned models. And as I mentioned earlier, you can throw hardware at this problem. You can run a model on a GPU, you can add servers, you can do lots of different things, and you will see significant improvements. However, it's also still not free. So depending on your resources, this might be the appropriate way to attack the problem at hand. It also might not be. And I'll show, this is another set of experimental results for another task. This one is about deciding amongst a set of candidate analyses, a set of candidate lemmas or pause tags, which is the correct one. And again, a deep learned model compared to a more dictionary-based one. And this is a little bit extreme. Again, these are fairly experimental results. But you can see that the speed delta is huge, and arguably, at least in the use case that we were working with, way outweighed the accuracy delta. And so these are the kinds of trade-offs that we're thinking about, that I think we all need to be thinking about in terms of choosing the appropriate solution for the problems that we're tackling. Next, I'm going to return to the question of data. So, again, speaking in very broad strokes, to get a deep learned model to perform kind of at its potential, at its highest potential, you need a lot more data than for a traditional machine learned model. And let's return to this graph for a moment. So basically what I would draw your attention to here is that to the right of, to my right, to your left of the red line, this is basically in the situation where maybe you don't have a ton of training data. A traditional machine learned model is actually going to perform slightly better than a deep learned model in most cases. And so, we've been seeing headlines like Google AI's AlphaGo is beating humanity at its own games, but let's remember that Google had 68 million training examples that powered the AlphaGo system. And so, if you don't have 68 million examples, and for many, I think, of the problems that we're all dealing with in this area of human language technology, we may not. There is a balance to be struck and a question to be asked about what the appropriate technology might be. The last thing I want to touch on is this idea of explainability. And I imagine that we've all heard this discussion of the black box problem. And here I have a tweet from someone, Pedro Dominguez, who writes, starting May 25th, this is from January of this year, the European Union will require algorithms to explain their output, making deep learning illegal. So this is a little doom and gloom, I would hazard. But it raises, I think, some really interesting questions. This is now maybe a little bit kind of more eloquently stated by Dr. Siddhartha Mukherjee writing in the New York Times. He's an oncologist. He says, "Here is the strange rub of a deep learning system. It learns, but it cannot tell us why it has learned. It assigns probabilities, but it cannot easily express the reasoning behind the assignment. Like a child who learns to ride a bicycle by trial and error and asked to articulate the rules that enable bicycle riding, simply shrugs her shoulders and sails away, the algorithm looks vacantly at us when we ask, why? It is another black box." So this is like a whole other talk that I'm not going to give, but it raises, I think, a lot of questions, especially for us in this room, who may be dealing with situations where there's a lot at stake, really kind of the definition of a mission-critical situation. We can remember that even as humans, subject matter experts, perhaps an oncologist looking at a foggy X-ray, we can make predictions that we may not be able to fully understand, but still feel somehow that is a justified decision. Can we ask the same of a computer? There's a lot to be said there. My point is simply that working in areas where there are high stakes, this is something to be keeping in mind. So, in conclusion, is deep learning appropriate for mission-critical applications? Hopefully I've demonstrated today that this isn't just a simple yes or no question. Applying deep learning to human language technology problems has the potential to bring great value to your customers and significant internal benefits to your organization. However, the process of integrating deep learning is not a guaranteed smooth sail. It's not yet the silver bullet. There's a lot of factors to be considered. So being informed, understanding the customer you're trying to serve, the problem you're trying to solve, the data you have available with which to address it, these are going to be the keys to your success, and choosing the best technology given what you know and what you have at hand. And so in that endeavor, I wish you the best, and I'm happy to take any questions.
We'll get a microphone over to you there. One moment, sir. To your right.
I have a question that I have based on the previous discussions, including yours. I don't understand the HLT's necessity because I'm not familiar with. I retired from CIA. Part of my work was a Korean linguist. Since you mentioned some numbers related to Korean language, I wanted to ask you this question. All this data and disambiguation and data search, etc., isn't that depend on the knowledge of the linguist, whether the translator knows the Korean language well enough, English language well enough, and then knows the facts like North Korean government structure, nuclear issues, that kind of thing. The more the translator knows the subject, all this work will become trivial, the way I think. So I was wondering whether you can explain about absolute necessity of human language, including the your learning method that does not really depend on how knowledgeable the translator is. Thank you very much.
Thank you. Let me make sure I understand the question. So it sounds like you're asking about sort of how does an actual human fit into this and their knowledge about the text and the translation process.
Yeah, basically, I have understood that human language technology is used and necessary in order to complement, supplement the lack of knowledge on the part of the linguists. Thank you.
Yes, okay, thank you for the
I
clarification.
want to know in what way human language technology is necessary if the linguists are, all 6 levels and then expert in the subject field.
Absolutely. So from my perspective, the issue here is really about scale. So knowing which documents are important to translate, it's going to take an army of very skilled people a great deal of time to determine, if you have a hard drive full of documents written in North Korean, which ones are just, someone asking, where they'd like to go for lunch the next day, and which ones actually have something relevant in them. And so I think a lot of our work is about making that triage process easier, so that your linguists can spend time on the problems that really are going to be high value. And so from my perspective, it's important that our systems be as accurate as they can so that they can, again, release staff from these kind of low value problems to, these mission critical ones. But as you said, there is always going to be a trade-off, and if you have an army of linguists, it is not clear to me, certainly, that we are ever going to be able to exceed their capabilities. I would just hazard that that's, again, it's just about kind of assessing where value can best be addressed.
Hannah, I want to give a completely different answer to the question Peter just asked. There is a very critical role for expert humans in this process, and that is in the preparation of the training material. If you go back to Kvir's presentation about fruit, how does the machine learning get started? It gets started by being taught what does a banana look like and what does a cherry look like, and that's the job of a person. The same thing applies to all of the text-related technology that Hannah spoke about. It all depends upon training material, and that training material has to be prepared by humans. So what's really happening here is we're using the machine learning and the deep learning as a way of amplifying the skills of those humans that annotate the training material. And that happens to be the subject of the next talk, which is how do we measure and ensure that annotators are giving the correct answers when they train. And I also have a confession I have to make. It turns out that we discovered earlier this year that some of our Korean training material had been misannotated. And it took us a while to discover that because we had to work backwards from poor results and poor scores that we were seeing, lower than expected, and figuring out why did that happen. And there was a failure to correctly align our annotation guidelines with the way the Korean linguists were annotating the training material. And that's where explainability comes in, being able to uncover when are the machines making mistakes and tracing that back to the guidelines that we give the human experts.
Well, Hannah, thank you very much.